the function ai fi and between li divided by norm of h goes to 0, and this will go to 0 if and only if the error of the original function and the linear approximation that we have here divided by the norm of h will go to 0. Okay? So since this is if and only if result, so what you can say is that it's sufficient. So if you want to compute the Fréchet derivative of vector valued function, it's sufficient to compute the Fréchet derivative of each component and just make a vector out of it actually. Just read it through and you can make sense of it. So here's an example. Here's an example. So I have a function f of x y equal to, say, x f of x y equal to x plus 2y, okay, x, y, and 2x plus y. So it has three functions, and I would like to find, what do you say, the Fréchet derivative of the function at point A. Okay? I know it has three functions, x plus 2y, okay, and f2 is xy, and f3 is xy equal to 2x plus y. Okay? And we know what is the Fréchet derivative of f1 of a, because it's a linear map from Rn to R, so it's itself actually. So in other words, if I want to apply this Fréchet derivative onto a vector h, this is same as applying f1 onto the vector h, and that is going to be h1 plus 2h2, because that is Fréchet derivative. And if you want to apply df2 of ah, okay, so we just computed previously, so this would be a1 h2 plus a2 h1, so this would be the Fréchet derivative of it. So the Fréchet derivative of f3 of a is equal to, what do you say? So it's going to be f3 of h. I must write h is going to be f3 of h, and this is going to be same as 2h1 plus h2. Okay? So the Fréchet derivative of the entire function, okay, if you are interested in computing it, what you can say is that you just compute df1, okay, operated onto h. So if you want to compute this, so you need to do df1 a operated onto h, df2 of a operated onto h, and the Fréchet derivative of f3 operated onto h actually, and then just make a vector out of it, that you have h1 plus 2h2, a1, h2 plus a2 h1, and 2h1 h2. Okay? If you are interested in writing it in the terms of x and y, just put x and y, just replace h1 and h2 by x and y, then you can have your function in more familiar format. Getting the point? Here is another interesting observation. I can write this vector as this. So 1, 2, a2, a1, and 2, 1 multiplied by the vector h1, h2. Right? You can write it also. So this would be what? So think about it. We will prove it. We haven't showed it yet, but we have a sketch that derivative. This derivative for sure is going to be a linear transformation. So if it is a linear transformation, this is the matrix of the linear transformation. Okay? So later on, what we will do, we will see that how to compute this matrix directly, so you don't have to go into all these details. Just directly compute it. So you can compute it like that, like the way you compute sine cut derivative cos or cos cut log of 1 over x, and so you can compute it with the same frequency. And this matrix has a name actually. So this matrix is called the Jacobian of the function A evaluated at A. Okay, so this guy is called Jacobian. So Jacobian. So the Jacobian is what? It's basically the matrix transformation or matrix representation of the linear transformation.
जो हमने जो तीन कंपोनेंट थे तो जब वो आपस में मल्टीप्लाई हो रहे हैं तो उसमें से ये आ रहा है लेकिन
किसमें मल्टीप्लाई हो रहा है?
x और y साथ में है उसमें से ये आ रहा है a1 a2 लेकिन सुपर वाले में भी h1 उसमें भी नहीं है
इस वजह से नहीं आ रहा because we proved actually that the derivative of a linear transformation is the function itself actually. Okay, function itself. So it's independent of no matter what point you choose. Okay, the derivative would behave the way the function itself behaves. So वहाँ पर एक ही जरूरत नहीं अगर आता तो हमें कोई एतराज नहीं because it so here's an interesting thing actually. So imagine you are sitting on a surface and you have this point actually, and I'm interested in computing that point, derivative, at that point. So why I'm calling it total derivative? So if this is what do you call f of a, the f of a plus h could be, so okay, so this might has a domain actually. So this is a, and a plus h can be where? So it would be a point corresponding to it. But it's really near corresponding to it actually. The question is this a plus h can represent almost any point actually here.
Yes.
Are you getting the point? So h is not just one direction actually. So h is arbitrary. So in other words, so h can be here. So this a plus h can be here. So it's just so this a plus. So if h is abstract, you are going from a to a plus h. That means that there is no what do you call restriction. So in other words, since if h is abstract, it means that it represents all points around the a actually. So no matter what point you choose, okay. And then for this a, okay. So this is my f of a. So I can have f of a plus h actually, and I'm interested in computing this difference, okay. And I want to approximate it with something linear. Okay, are you getting the point? So that linearity is what is basically this transformation actually. Now I'm saying that since a is this and h can be anything, so I can go in any direction. So in other words, I'm not only getting this change, linear approximation for this change, but since a plus h can be here, so I'm also getting a approximation for this change, and all kind of changes actually, no matter what direction you go actually. Okay. So this Fréchet derivative is like, you have a point and you are computing Fréchet derivative at that point, like kaboom, you have change in all directions at once actually, because h is arbitrary. Okay, so there is no restriction actually. So therefore you call it a total derivative. You are computing. So if this Fréchet derivative exists, that means that sitting at the point A, you can compute the change in the function in all possible directions actually, because h can be anything. Is it making sense? Okay. So that's what the power of it is actually, that it not only just, so it doesn't giving you change in the direction along h actually, but it gives you, since h is arbitrary, that means that it gives you change in all directions. Okay, wherever you like to, whatever h you like to choose. Okay. Is it making sense? Thoda. Okay. Then I would like to prove some properties of the Fréchet derivative, and maybe just talk about some properties of the Fréchet derivative. Okay. So I have derivative. Does this derivative? So when you learnt derivative in one dimension, what you learnt after after computing the derivative by definition? Okay, what was the next thing that you learned in your theory of differentiation? Huh? So you learned chain rule, and then you learned product rule, quotient rule. Are we going to have all these things here? The answer is why not? Okay, we are going to have all these things here. So let's prove some of those properties. Okay? So the rest of the chapter is just in the praise of this, creature that we have created actually, this species, Fréchet derivative that we have created actually, that what miracles this guy can do actually. Okay, so we're gonna rest is basically define ki ab tareef karni. So what is the most elementary theorem that you have learned about the differentiation when you learn, for example, calculus, 1D calculus? Most elementary theorem, pehla theorem. Exactly. So the function is differentiable at a point, then it must be continuous. So the question is, do we have the same thing here? The answer is yes, actually. So if f is differentiable at a, okay, by differentiability, what do you mean? So what is the meaning of f is differentiable at a? F is differentiable at a if and only if a good linear approximation exists. Okay? If f is differentiable at a, then f is continuous at a. So help me out, how do we prove? Do you recall? Do you remember the proof in the one dimension?
Yes.
What is the proof in the one dimension? So I want to prove that the limit x goes to a, f of x minus f of a must be 0. That's what I would like to prove. Huh?
Yes.
So हम क्या करते थे? Okay. So I want to prove this to be 0. So I know this is differentiable. So divide by x minus a and multiply by x minus a. Okay? Divide by x minus a and multiply by, and then take limit separately. So if we take limit here, so this is f prime of a multiplied by limit this, which is 0, so we get a 0. And what does this shows? This shows that limit x goes to a, f of x minus f of a is 0. So hence the function is continuous at a point actually. The question is, can we develop a similar proof here? So what we should do? Okay? From now on, other darling. I mean, if you want to do good mathematics, don't accept things without proof. Unless, okay, sometimes, proofs are beyond our level, so we just assume that from now, okay, we may skip them. But usually, I mean, you have to always think that, okay, whatever you are saying, you should have a justification for it. Okay? So what I would like to do, I would like to compute this. Limit x goes to a, f of x minus f of a. And I want this difference to go to 0. Thing would be a bit interesting here. Okay. If I define h to be, you have to keep in mind that this f is a map from Rn to Rm actually. Okay? So it's not just a simple map actually. So whenever I write f, it's not a map from R to R, but it's a map from Rn to Rm. Okay? So h is what? So take h to be the difference of x minus a. Okay? Take h to be the difference of x minus a. So I can rewrite this. So what it would be, what this limit would become?
Plus h.
We're going to say h goes to 0, or maybe the limit norm of h goes to 0, okay, and f of x will become f of a plus h minus f of a. So now we have got something that we know. Okay, so what should I do?
Now is multiply divide.
So here's the thing. So what I need to do, I know this guy is equal to limit norm of h, okay, what? L of h, because f is differentiable, so there must be a good linear approximation that must exist such that f of a plus h minus f of a should be L of h plus the error E f L actually, okay, so you have a and h. Okay, so this is what is going to happen. So I want this go to 0. So what do I need to do? So what can I do? Is it sum actually? Yes. So I should do what? So limit divided by the norm of h and multiply by the norm of h.
Yes, sir.
Okay. So this is the trick that we can do. So if this is true, now since function is differentiable, so this goes to 0 as norm of h goes to 0, so this guy is 0, and multiplied by something that is 0, we have plus 0. How about this one? So if norm of h goes to 0, that means h is tending to become a 0 vector actually. So we know the first property that you learn when you learn the linear transformation, that the linear transformation is something that maps always 0 onto 0 actually. So we expect this to be 0 and hence you expect this to be 0 and hence what do you want? So you have it. Okay? You have it. So limit norm of h goes to 0. F of a plus h minus f of a is 0. Okay? So we proved it. But this is same as this actually, isn't it? ठीक बात है ना? ठीक है? So I can return back. So I can say a plus h is like x, f of x minus f of a, and limit h goes to 0 means x goes to a actually. Okay? So this completes the proof. So if the function is differentiable, it must be continuous. Okay? Why it's continuous? Because the limit of the function is equal to the value.
स्केलर फंक्शन को करने से भी यही प्रोसेस है
जी
स्केलर फंक्शन है वेरिएबल है आपके उसमें यही जो प्रोसीजर है प्रूफ
you're almost doing the same thing. Okay, but there is an additional layer of complication because the way we have defined it actually. Okay, so in the previous proof that we did for the one dimension, there was no linear approximation and all that, so it's simply divided by x minus a and multiplied by x minus a. Well, in higher dimension, you have to, make sure that you have.
So as we are using the definition, doing the things. So in one dimension, we had lot of things like the differentials of trigonometric functions, exponential functions, and other functions. Can we do in this higher dimension?
100% we can do it. So every rule that works there works here as well. 100% we can do. So that's what we are heading actually. Okay? I want to get rid of this technical definition and I want some quick way to compute the derivative, the way we are lazy, the way we like to do things was x power n is n times x power n minus 1, So that's it. So we are heading towards such kind of things. Okay? The next theorem, I'm not proving it. I mean, I highly recommend that you should, at least see the proof of it at least once in your life. Okay?
सर यहाँ पे सर हमारा यहाँ जब नॉन जीरो हो रहा है तो सर h में जीरो हो रहा है तो सर ये h अगर जीरो हो रहा है तो हम वही पॉइंट नहीं उठा रहे सर a और h में चेंज नहीं रहे सर a ही उठा रहे हैं.
Okay, so I can see what you are saying. So तभी तो कह रहे हैं ना, when x gets to a का मतलब ही यही है, okay, that x is an arbitrary point but really near to a actually. Okay, when h goes to 0, what does it mean? So you are really near to a.
कुछ तो different है ना, ये x 0 हो गया यहाँ.
Okay, so you are okay. You are not convinced that this must be okay, this must be 0. I think okay, here's the thing. Here's an argument. Every linear thing is continuous.
Very linear thing.
Okay? Every linear thing. So the linear functions are continuous. So we proved it in the first semester, first chapter actually. Okay, that if you have linear things, they must be continuous. Okay? So L is linear. So if it is linear, the limit is equal to the value.
यहाँ पे हम ऐसे लिख सकते हैं कि L अगर Rn से Rn और L linear है, हम लिख सकते हैं L x equals cx1 plus cx2.
So that's what I'm saying, that by linear I mean a linear polynomial actually. So if L of h is a linear, that means L is a linear polynomial, and linear polynomials are continuous functions. So if it is a continuous function, the limit equal to the value. Okay. Now you can say, okay, ये एतराज़ करेंगे, so shall we put norm of h goes to 0 here or what? So what you can say, that when I'm saying that norm of h goes to 0, I mean that the vector h goes to the 0.
h1 and h2.
That's a good question. You should always ask such questions. Okay. So the next thing that I would like to do is chain rule. And as I said, you at least read this proof at least once in your life. मेरे जो है खबर में ना पूछने फरिश्ते हैं कि भाई क्या किया सारी जिंदगी में, मैथ पढ़ी, चेन रूल किया, पढ़ा था, प्रूफ पढ़ा था, नहीं लाओ मुझे था. So I'm not proving it. It takes a lot of time, but it's a readable proof. You can read it easily.
So we have tried one dimensional integral, but it will not got that in second semester. So
You haven't even proved the one-dimensional.
no sir. We have tried, but sir, it was then up 2 page at
Wait for the real analysis. Okay? Wait for the real analysis. There is also a proof here. Okay? I mean, if you go to the end of the page 33, so I think you have a proof here. No, proof नहीं है, just using it. But it would be a huge deviation if I start doing the one-dimensional proof here. Okay?
Composition के शुरू करते हैं सर.
So for now, you may assume that.
Chain rule लागू सर. Composition के शुरू सर.
You can do it actually. Think about it. So what you want to do is that you want to compute the G composition F at the point A actually. Okay? So this is not theorem. And where G and F are one-dimensional functions actually. Okay? So that's what you would like to compute. So what you need to do. So you have to compute G composition F operating on the A plus H minus G composition F operated on the what A and divide by the I'm talking about one dimension, and then divide by H and then try to compute the limit actually. So you have G of F of A plus H minus G of F of A, and do something with this G and try to show that you have the derivative the way you want actually. Okay? We can get into it, but at the moment I'm not getting into it. It's not a big deal. I can show you the proof. You can read the maths for yourself. Okay? If you're still interested, you can come in my office and we can prove it. Okay? So I don't want to spend a lot of time on proving things. Take a So here's a beautiful, powerful theorem which says that if you have a map from Rn to Rm and G, so after the class you can come with me in office and then we can prove it. Okay?
So one वाला भी 2 one dimension में भी 2 में भी दोनों प्रूफ हो जाएंगे.
One prove करेंगे 2 आपको.
one हम सोचते हैं 2 आपको करवाएंगे वो भी.
खुद करके आए फिर
I mean, even if you read here in book, it says it's optional. It says it's optional. Okay. But you know, now you know how to read the math. So just see that what this guy is doing. So the calculations are right in front of you. And if you get trouble, just do ask me. But you know, this is something that you should do for yourself. Okay. So here's the thing. So F is a map from Rn to Rm, and G is a map from Rn to Rp. And suppose that Uncle F is differentiable at A, and Uncle G is differentiable not at A but f of A, to which I am giving that name B. Okay? Then what would be G composition F? What would be the Fréchet derivative of G composition at F evaluated at A? Okay? Now, what we're going to do, that you extremely analog to what you did in one dimension with a slight difference. What I need to do, compute the Fréchet derivative of F at a point. Compute the Fréchet derivative of G at what point?